Thank you for the introduction. Thank you for the invitation. So I'm going to talk about fullerenes, counting them, and doing so with fancy math. So here's a picture of sort of the archetypical fullerene. This is Buckminster fullerene. It's a molecule. It's each little green vertex is a carbon atom, and there are 60 green vertices on a soccer ball, and that explains that 60 there. And it's very symmetric. So the group of symmetries is the icosahedral group, and that's what the IH is doing. So this is the name of this molecule. Here's some pictures of it. On the left from a transmission electron microscope, and on the right with an optical microscope. Those platelets are about 10,000 fullerenes across, and on the left you see a single fullerene. So brief summary of the history of this most interesting of the fullerenes, C60. We highlight that, so the 1985 discovery, Kroto, Kroll, and Smillie won the Nobel Prize for that. And then in 1990, this is produced for the first time in large quantities, large meaning on the order of grams. And this was done in Heidelberg by Wolfgang Kretschmer and this group. This picture on the left, I think, is the evaporator that they use to produce it. So my understanding is that they start with a graphite rod and zap it and evaporate it. And in the soot that settles, you find fullerenes, and they figured out how to extract. On some 1 or 2% of the soot is fullerenes, and you find out how to extract it. And then it has various macroscopic forms here of fullerite and this characteristically pink fullerene solution. And people were very excited about it around this time. It started turning up all over the place. In particular, in 2010, it was found in outer space and planetary nebulas. Okay, so that's C60. So that's the smallest fullerene. And really, this talk is mostly about larger fullerenes. So let me gradually lead you into this concept. So here you see a histogram of atomic masses of particles observed in that vapor immediately after you vaporize the carbon rods. Carbon has atomic mass of 12. So to translate between these numbers at the bottom and the number of carbon atoms, you divide by 12. I think you can see here that what we're seeing are mainly molecules bigger than, with more than 60 carbon atoms. If you look at this close up, maybe you also notice that there's always an even number of carbon atoms in these molecules that you can see through mass spectrometry in the vapor. And that's what I want to talk about, is these bigger guys. So first question, well, I mean, what are they? What are these clusters of carbon with more than 60 carbons? And basically the answer is they look like this. So these are pictures made by the Bucky Gen computer program of larger fullerenes, well, some smaller ones and some larger ones. Starting with the dodecahedron is A, the soccer ball we've seen before is B, and then they can get bigger and bigger. And this is really what I'm going to study as a mathematician, these pictures. So let me define in the chemistry sense what a fullerene is, and then I will clarify exactly what I'm going to study and count. So a fullerene, for me, is really a molecule made of carbon atoms, but it should have this geometric configuration where they're arranged on a surface, and they should be at the vertices of a tiling of the surface by pentagons and hexagons. So in this picture, the blue guys are all pentagons, the orange guys are all hexagons. And I've called it a topological sphere. By that I mean that, well, it's the shape of a sphere, but it's topological, so it can be stretched. It doesn't necessarily look like a round sphere. All of these shapes are of interest. Okay, and I want to kind of make the point that even chemists should be interested in this. So why study large fullerenes? What are some reasons you might be interested in these? With the caveat that for the most part, these big ones, we can't really get our hands on them. It's hard to synthesize and isolate anything other than a few relatively small, relatively symmetric fullerenes. Okay, so the first reason is to understand how the small, stable, symmetric ones are produced. And this could be either in outer space or in the lab. My understanding is that there is some pretty fundamental open questions about this. Different kind of proposed mechanisms for getting one of these beautiful balls, either building it up kind of one carbon at a time, or folding it from a sheet of graphene, or this proposal, which I like, is maybe you can start in that vapor with a larger fullerene, and through various kind of local chemical processes, like your kind of C2 pairs, loss of a pair of carbons, you decrease the size until you reach something more stable. And obviously this is a process we'd like to understand, and for that purpose, we'd be interested in these larger fullerenes. Here in the lower left, I have just the simplest picture of what one of these local modifications can look like. So here, if you imagine starting with a configuration represented by the green lines in that little picture on the left, and it could turn into the configuration with the red lines, and you see that both of those indeed are a tessellation of the patch by pentagons and hexagons, if you count the sides, where two vertices have disappeared. Also, I'm told, I don't want to be making this claim myself, I'm told that fullerenes are slightly not in fashion as much as they used to be, but carbon nanotubes and graphene are both very hip, and these you can view as some sort of large limit of fullerenes, right? If you have a sort of an infinitely large fullerene, either it could look like a flat sheet, or if it got really long like this, it could look like a carbon nanotube pictured on the left, and in A on the right, you see a patch of graphene. And there's something else that I recently read a Quanta article about called Fuller tubes, some approximation of nanotubes that are actually examples of large fullerenes that I think have recently been synthesized in the lab. So, yeah.
What does the D mean?
The D. C's carbon. So remember the IH was the symmetry group. So this is the Schoenflies notation of point groups in space. D5H is a different symmetry group. It's a dihedral. D stands for dihedral.
Okay, so it's 90 molecule. No, 90 atoms, 90 carbon atoms. And
yep.
D describes the symmetry.
The symmetry group, exactly. Yep. Finally, endofullerenes is a word for a fullerene containing something else on the inside. In fact, you can have fullerenes containing other fullerenes on the inside, described as kind of carbon onions. And these you can obviously have larger fullerenes in that setting. Or, yeah, there could be other reasons. Heterofullerenes, larger carbon structures. Okay, so now that's my chemistry. So on to math. I'm going to define more carefully what a mathematical fullerene is. So the first way you could approach it is kind of through graph theory. Here, you take your soccer ball in this picture A, and I just want to remember the vertices and how they're connected. And from that point of view, well, actually, it's probably easier to draw a two-dimensional picture than a three-dimensional picture. So I may as well project my soccer ball, as is demonstrated there, onto the plane. And I get just a graph. So it's a trivalent graph with a planar graph where the faces are pentagons and hexagons. I'm going to call this object a combinatorial fullerene. On the other hand, I could say, well, really, I want a slightly better mathematical model of what's going on. Really, I'd like to study convex polyhedra, whose boundaries are pentagons and hexagons. And maybe I'd call that a geometric fullerene. So the first math theorem that I want to tell you is that these are the same. So this is a theorem of Alexandrov, 1942. And it's more general. This is a special case. He certainly wasn't thinking about Fullerenes, but it says that every just combinatorial trivalent planar graph with faces, pentagons, and hexagons is realized uniquely by a geometric Fullerene. So this is the sort of theorem that, you know, gets mathematicians excited. Now you have a combinatorial way of counting or studying something geometric. And so instead of these words combinatorial and geometric, I'm going to refer to this thing, which is both of these, as a mathematical Fullerene. And okay, I had one more chemistry slide. So roughly, mathematical Fullerenes do correspond to actual Fullerenes. I put some caveats here. The first one is a very minor one, but if you can actually, the edges won't all be the same length. Some of the bonds will be shorter than others, and for the most part, you can actually predict which bonds will be shorter. Here's a very close-up picture. Half is, you know, is half a nanometer scale of a hexagon bond. You see something very different. And then, you know, when we're talking about actual Fullerenes, we're talking about critical points of the energy on some large space of molecules, and it's hard to model that really by a purely combinatorial mathematical model. So indeed, some Fullerenes can kind of relax into more than one minimum of energy. Some can't at all, some can never be stable. One thing I wanted to say about this is that there's a heuristic criterion for stability that will come up in a later slide. If you have two pentagons next to each other, then it's very unlikely to be stable. So a tiling where no two pentagons are next to each other is said to satisfy the isolated pentagon rule. And at first approximation, it's probably more likely to be stable, to actually exist, correspond to a real Fullerene. Okay, so this talk, I want to talk about two questions. First, how many mathematical Fullerenes are there? Well, there are infinitely many. They can be arbitrarily large. So to be more precise, for each positive integer, for each number n, how many mathematical Fullerenes are there with n carbon atoms? And now I claim this is a number of graphs. It's a finite number, maybe a large finite number, but this is a finite number, and so we can study it. And then if I get through that and still have time, I want to say what they are. Okay, question one. Our second math theorem of the talk is due to Euler in 1758. And he also wasn't thinking specifically about Fullerenes, but he proved that the number n of vertices in a mathematical Fullerene has to be even, which is an explanation for, in that histogram you saw, why we only saw an even number of carbon atoms in the weights that were observed in the vapor. Meanwhile, that first part of Euler's theorem also has an explanation, and the explanation is the second part of Euler's theorem, which says that you can calculate how many hexagons it has to have and how many pentagons it has to have. So the hexagons there's always n over 2 minus 10 hexagon faces. Okay, so that would be nonsensical if n wasn't even. But maybe the even cooler part is there's always exactly 12 pentagon faces. Examples of, you know, checking this theorem, we can check it in two cases. The dodecahedron on the left has 20 carbons, 20 vertices, and 20 divided by 2 is 10. Subtract 10, you get 0 hexagons. Indeed. On the right, C60 divided by 2 minus 10, you get 20 hexagons, which is the number of hexagons in a soccer ball, if you've counted. Okay, so let me now talk about the history by people who really were thinking about Fullerenes, not just older theorems that we can apply. So for the rest of the talk, I'm going to call F of 2n. F stands for Fullerene. The number of mathematical fullerenes with 2n carbon atoms. And for sticklers, I want to count mirror images as distinct. You could decide either way on that one. All right, so in 1991, two chemists, Monopoulos and May, tried to write down on all of the fullerenes. And in particular, this would give them a count. And they had a clever method. So you start at a pentagon in your model, and you start peeling your fullerene like an apple. And you get one of these things, which they call the phase spiral. And if you record, so this is fairly a canonical way to sequence the faces of the fullerene, and now you can record which ones are the pentagons. So you get 12 numbers. Now you can try to figure out which possible combinations of 12 numbers really give you these trivalent combinatorial graphs, and which ones give you the same fullerenes. And you can, through a lot of bookkeeping, try to get a count for fullerenes. There's an issue with this method, is that not all fullerenes are spiralable. So this one on the right, if you start peeling it like an orange, you'll get stuck, or you've got stuck at face 15 before you visited face 16. In fact, there exist fullerenes that are not spiralable from any pentagon, so you kind of can't count with this approach. In the 90s, there were some more proposed algorithms to count these, including tweaks on the space spiral algorithm that let you get around that issue. And then in 1997, the computer scientists got involved. They came up with a completely different algorithm, which is actually kind of, to me, looks more like the molecules might want to count themselves, meaning they kind of invert this C2 loss process that we saw in the pathway and try to count larger fullerenes by building them up from smaller fullerenes by making local modifications. So what you can imagine is that you have some finite set of possible modifications from each small fullerene that will increase its size. And now you can imagine making kind of a graph going up with these edges representing the modifications. If you choose canonically one modification of the set of possibilities at each stage, then your graph is a tree, and you can enumerate all fullerenes or count fullerenes just by kind of counting layers of the tree. And so they came up basically with a way to canonically choose one path on this graph leading to each fullerene. And this is their method of counting them. It was more efficient. It let them get compute F of 2n up to 214. 2012, they revisited this. Actually, it was a little tricky. They made mistakes before up to after C136. So they corrected those in 2012. They called it a typo-like mistake. I don't know exactly what that means. I don't know exactly how far they computed in 2012, but last week my co-author emailed Jan Gojeber and asked him to run the algorithm again. So in 2012, they were able to run it and calculate F of 2n up to 2n equals 400, up to 400 carbon atoms. What's that? Ooh, I wish you hadn't asked 400 specifically, because just for the typographic reasons, I had to cut the table off at 328. But here's the answer for 20 to 328. Yeah, so you can see these grow pretty fast. It's not exponential growth, but it is a lot. At the beginning of the chart, you can see our friend the dodecahedron being that one with 20 carbons. At 60, you see there's already 3,000 with 60 carbon atoms. But Buckminster fullerene is the only one with the icosahedral symmetry group. It's also the only one satisfying the isolated pentagon rule. And yeah, that's the table. That's what we saw. the growth actually is fairly precise. So a mathematician, Thurston, in 1998, proved, as a consequence of sort of a much bigger theory, that f of 2n grows approximately like n to the 9th power. And here approximately means there are constants, two constants, so that there's a lower bound times n to the 9th and an upper bound times n to the 9th, and it's sandwiched between those. Here's a graph of this number, a log-log graph. So if it was actually like n to the 9th, this should be a straight line. And it looks pretty much like a straight line. Actually, there's an interesting thing which is kind of obscured by the choice to use pluses on this graph instead of little dots. But there really are two different constants. So it's not converging to a constant times n to the 9th. It's wiggling between two constants, but those two constants are really close. One is like 1.002 times the other one. So they differ by a factor of 1 in 500. Okay, so why? Well, that phenomenon is explained by a theorem of myself and Phil Engel in 2017, where we gave a formula for the leading term of this function, the number of Fullerenes. So I'm going to go into this formula on the next slide, but while it's here, I want to introduce this notation here. I've written a sum over d line n. That means a sum over all the divisors of n. So a sum over all the positive numbers d, so that n over d is also an integer. Okay, and so what was going on here? Well, let's call this, actually, I'm not calling it that. This is a well-known thing you can do to a number, sum its divisors to the 9th power. This gives you E10 of n, well known to mathematicians. And in case you were confused by this dividing thing, here's what's going on. So for instance, to compute E10 of 4, the divisors of 4 are 1, 2, and 4. So you take each to the 9th power, you add them up, and you get this number. E stands for Eisenstein. Gotthold Eisenstein was a mathematician from the 19th century. He died when he was 29, like many mathematicians then, seemingly. And he showed that this is an example of something called a modular sequence, that I'm going to call a modular sequence. Actually, I wanted to say one more thing about these two constants, looking at the previous line. So one thing I want you to take from this calculation of E10 of 4 is that E10 of 4 is actually very close to 4 to the 9th power. Because whenever you take something like a divisor of n, it's like at most n over 2, and the 9th powers really exaggerate the difference there. In fact, a first approximation, E10 is just n to the 9th. A slightly better approximation, if n is odd, E10 of n is about n to the 9th. If n is even, E10 of n is about n to the 9th plus n over 2 to the 9th. And if you take 1/2 to the 9th, and you're good at powers of 2, you see that explains the difference of about 0.002. Okay, so going back to modular sequences. So modular sequences are very cool. They're really called Fourier coefficients of modular forms, but just shorten that to modular sequences. And it's a property of a sequence of numbers. It can be modular. Actually, it's a set of properties. So for every weight and every level, you can be modular of weight k and level n. So come up in a sec. And it's a really subtle property of a sequence. It's not easy to check. Really, it's a property in terms of the generating function of the sequence, but which is a fancy way to say that it's a condition. To check the condition, you have to sum like infinite sums, recombine the terms of the sequence in infinitary ways and check that they're equal. So it's subtle and therefore deep. has in particular deep connections to number theory, which is the study of prime numbers. And mathematicians love these. Okay, so what do we do with this? How do we prove this is really what I want to say. We actually we weren't studying Fullerenes at the time. We were studying something slightly different. This other sequence, which I won't define, which we'll call for now F bar of 2n. But we observed that F bar of 2n is very close to F of 2n. The difference is smaller than n to the ninth. And then we showed that F bar of 2n is this constant times the Eisenstein series. And how did we show this equation here? This is the proof. Okay, first, we prove, using some big theorems, that it is a modular sequence. So the modular sequence of weight 10 in level 1. Well, it's well known that every modular sequence of weight 10 in level 1 may not be equal to E10, but is equal to E10 up to a constant. So all we had to do then was figure out that constant. How do you figure out the constant ratio between two sequences? Well, you just pick any number, you evaluate, you find the correspondence at that number, and then that constant ratio has to hold forever. So we picked a number, evaluated it, and found this constant 809 over this large denominator. Again, so that was where I was going to end when I offered to give this colloquium. But just 2 weeks ago, we have a new result. Again, as Anya mentioned, this is inspired by discussions with her. We realized that actually this F of 2n is also, well, modular, but of a much larger level. So in a more complicated way, but it should also, the same idea should also let us figure out this sequence. Okay, and so what does that idea mean? Well, for weight 10 in level 1, it just so happens that modularity just depends on one parameter, that constant of scaling. For any weight and level, it's still true that there are only finitely many parameters that parameterize the whole space of modular sequences of that weight and level. And so with some work, we were able to get this number of parameters down to 150. And now we use the key that 150 is less than 400. So using the table that Jan Goteberg sent us, we determined F of 2n, this full sequence, from solving a linear system of equations, finding the value of its parameters, knowing 150 of its values. And this is what we got. So this is the answer. This is how many Fullerenes there are exactly, mathematical Fullerenes with n2n carbon atoms. You'll hopefully recognize that first term is the asymptotic term that we had before. So all of the subsequent terms are growing at most like n to the 8th. And actually they're all some modifications of the first term. So they're all of the form, you take n, you factor it, you write down all its divisors, and you do some easily computable thing and sum it up. So this is computable, and it's exactly as hard to evaluate f of 2n as it is to factor n to find its divisors, which in particular means if you care about any value of n smaller than the number of carbon atoms in the universe, we can tell you what f of 2n is. Yeah. For instance, maybe you care about 10,000 carbon atoms, then there are this many Fullerenes. It's a lot. Maybe some of those digits are no longer interesting to chemists, but they're still interesting to mathematicians. For comparison, the previous result, the asymptotic result, gives us already something which differs at the third digit. So, yeah, fairly big difference. with the precise result. So, okay, can I convince you that an asymptotic formula, that an exact formula rather, is worth more than an asymptotic formula? I guess the first argument I would give is that actually, by the previous slide, they actually differed by a fair amount. And so for some asymptotic calculations, you can actually notice the difference. Maybe if you want to somehow understand some asymptotic limit of chemical fullerenes, the large n asymptotics of this might come up. I don't know. Okay, but here's a more precise reason. Why would you care about this exact formula? Well, it's the first thing that we've been able to make, which would check that the algorithm of these computer scientists is really counting the right thing, because it shows that it's consistent with itself. They calculated these numbers, and their table does satisfy this. I mean, we use the first 150 to determine the parameters, and then we use the next 250 to check them. And so I think they didn't make a typo this time. Okay, but then it's also interesting because modular forms are interesting. So, and here we've written something in terms of a modular form, but, and the first time we did this in our first paper, we calculated it by hand. We figured out the constant by hand. This time we're mathematicians. We're not that good with computers. We never would have done this by hand, computing the table out past 150. And so it's only because this was an interesting chemistry problem, which inspired these computer scientists, that we were able to get this mathematical formula using their tables. So for instance, if you look at the digits past the ones where you stop reading, these have some interpretation, which I haven't explored yet because this is 2 weeks old, but some number theoretical interpretations. This gives some relation between fullerenes and prime numbers. Okay, and that's the answer to question 1. That's how many. So for question 2, what are they? I'm going to point out some things. So first of all, what are they? You could rephrase in terms of like, how should you name them? I mean, what are they? What format do you want the answer? And meanwhile, a naming system is a lot like an algorithm for writing them all down. So both of the previous enumeration attempts give some answer to what are they, and but not all answers to what are they are the same. So a good naming system should have certain properties. It should make it easier to understand conceptually what they are as well. Okay, so what's the story? How do you, I mean, chemists, when they study molecules, they like to have names for them. They publish these big books about what to call molecules. And for fullerenes, they kind of throw their hands up. So the official naming recommendation, as far as I understand it, for Buckminster fullerene, for instance, is this guy, C60IH, and then we've added this 5,6, which is just superfluous information referring to the size of the pentagons and hexagons. And we got lucky with this one that it happens to be unique, but the only information you're seeing here is the number of carbon atoms and the symmetry group. So clearly this is not going to distinguish fullerenes that are larger, that are much larger. Okay, so the one attempt at coming up with a canonical naming system is to use phase spirals. So you write down this list of 12 numbers, which is the order that you see the pentagons in. And I guess in 2014, they maybe ironed out some of the issues with phase spirals and wrote down a canonical name for each fullerene based on this. And similarly, the patch replacement algorithm should also give a canonical naming system. I don't think anyone's worked out exactly how that works yet, or they've made tables, so maybe it's the same thing, but that should work. Oh, sorry, but both of these have a sort of conceptual problem to me, which is maybe easiest to talk about in terms of C2 ejections. This is a small perturbation of a fullerene, which is chemically relevant, but it can change the name a lot. Especially it's easy to see with a phase spiral. If you perturb two little things down here, that can just throw your naming all out of whack. And so there's not this kind of continuity of names with physical structure. Patch replacement, I think, is a little better, but I think there's a best way to name them with this property suggested by this paper of Thurston. So I want to try to explain that a little bit. Okay, so mathematically we can rephrase this as, you have the sphere with hexagons and pentagons, and I want to tell you where the pentagons are. And that's how I'm going to name the combinatorial structure, the mathematical structure of this. But where are the pentagons? I don't know. Where do you start from? How do you measure? So this is what Thurston proposes to answer. Okay, so what really helps in naming things, especially two-dimensional things, is to have them actually on a plane, because then you can use coordinates. Now you can try to take your sphere made of pentagons and hexagons and kind of lay it out on a plane. But it won't fit that nice. I mean, pentagons and hexagons don't really fit together on a plane. So here's the first trick, which chemists already use this trick, I think. It predates Thurston, is to dualize. All right, so that means you take your graph here, you replace every face with a vertex, and you replace every edge with an edge crossing it, and every vertex with a face. And so now instead of a trivalent graph, you have a triangulation of the sphere. So obviously we've lost some kind of, carbons are no longer points in the dual, but we were trying to record the locations of the pentagons, and those now are points. Even better, if you take now a triangulated sphere and you cut along the edges of the triangulation and unfold it. If you have triangular graph paper, you can always lay it down so that the triangles match on the graph paper. And now you can record here what are the orange vertices by, well, a pair of integers, which lattice point in the triangular graph paper they land on. All right, so this is great, great progress. But there's still the problem that, there's so many ways to cut open a polyhedron and lay it flat on a piece of paper. This is not yet giving us a canonical way to name something. So that's the second part, and that's also the second trick. So the second trick is to realize that you don't need to cut it along the edges. You can cut it along, say, any straight lines, maybe which traverse triangles. And so here's how Thurston says you should canonically cut your dual fullerene. Well, you measure the distance just as an ant would walk between every pair of orange vertices on your dual triangulation. You find the one where the sum of the distances to all the other ones is smallest. And then you just cut along those straight lines to all the other ones. Now you open it up like a star, like this yellow star, and lay that down. It's still, so the edges now may cross, in the middle of the triangles on your graph paper, but the vertices will still map to the vertices on your graph paper. And all we wanted to record anyway was these locations of these vertices. Okay, so you take these vertices, they correspond to points, and now you have to pick one. I don't know how you pick the one, but you start at one, go around the outside, record how many how many triangles over you have to move, one way of recording that is to pick a basis for two edges of the triangle and write each of these differences in that basis, which I've done here. Then it takes 10 numbers to, well, 10 pairs of numbers to describe a Fullerene in this way. And so if you like, you can write that as a single list of 20 numbers. The A coefficient and the B coefficient of each of these things. And so this gives you a list of 20 numbers, which records a Fullerene. So, okay, for now, this doesn't seem like a simplification. We started with a spiral algorithm, which recorded it as a list of 12 numbers. Now we have another algorithm, which records it as a list of 20 numbers. Is it really any better? Well, what I claim is that this is the right way to record it, because not only do most, so two properties. One, most like C2 modifications don't change the name very much. And the few that by necessity have to, for instance, if it like changes which vertex is closest to all the other ones, it changes it in a predictable way, in a way that you can understand. So this is the way that gives geometric structure to the space of Fullerenes. And let me show a sketch of what that geometric structure is. So, okay, this is 3 dimensions. I didn't draw 20 dimensions, but imagine that these points are just a lattice filling out 3-dimensional space. There is some, well, imagine 20-dimensional space. There is some cone, think of this purple cone, starting from the origin, going out, so that the allowable sets of 20 integers, which correspond to Fullerenes, are exactly the intersection of this cone with this lattice. So it's the lattice points contained in the cone, the ones that I've shaded in purple here. Moreover, the edges of the cone, actually, you can kind of write down what they are, and there's you can make sense of kind of going off one edge of this cone, and it takes you maybe in a different edge of the cone. And so there's really more complicated mathematical structure here. So another way of saying that is that if you look at, oh, maybe one thing I wanted to say also is that sort of the distance of one of these points from 0 corresponds to the number of carbon atoms in this picture. Okay, so here's a hint that there's some, higher level of math here. So if you take some Fullerene, if you cut it as Thurston suggested, starting from the shortest guy, you get some point in this purple cone. But if you cut it in any other way, you get maybe a different sequence of 20 numbers. And you look at all possible ways of cutting it, you get a bunch of possible representatives. Maybe think of those as being these black points in the picture below. And then you sort of, as you move off one edge of the cone, you can see the set of black points where you pops in another edge of it. Okay, so this is a space that, this way of thinking about it is, first of all, the reason why we're able to make a connection to modular forms. So it was already useful. And I hope it can be useful for some other things too. Maybe for visualizing some, chemical properties even of Fullerenes and how they depend on the structure. Or visualizing these pathways of formation. There's paths in this cone. This would be a cool thing to do. Okay, so all of these ideas and hopefully many more will be the focus of this HITS lab project with Anya Granova. And also we have a PhD student coming, working on applying math to carbon chemistry, exploring this further. And I will end there by thanking HITS for its support of interdisciplinary research, which can be a lot of fun.